Mitigating insect attraction with geometric and spectral light design. Background: artificial light and insect attraction. Artificial lighting at night, Alan, is known to disrupt insect behavior and ecology. In particular, shorter wavelengths, ultraviolet, and blue light, are highly attractive to many nocturnal insects. Studies have shown that using longer wavelength lighting, for example yellow or amber LEDs, drastically reduces the number of insects drawn to a light source. In essence, the bluer the light, the more insects it tends to attract. Beyond spectrum, the intensity and distribution of light also play a role. A light that radiates broadly into the environment will lure insects from a larger area, whereas a shielded or directed light affects a smaller zone. For example, research indicates that a diffuse fixture spreading light 75 degrees wider can attract about 16% more insects than a more focused, directional fixture. These insights suggest that both the spectral content and the geometric distribution of light are critical factors in designing insect-friendly or insect-suppressing illumination. Problem scenario: a magenta porch light in a bright coastal setting. Consider a coastal porch equipped with an upward shining magenta lamp recessed in a cavity. Imagine a porch light shining upward into a colored shroud, rather than outward. The porch is located near a coastline and there are numerous other light sources in the environment, 7 ambient sources, as described in the transcript, which might include things like city sky glow, moon or starlight, nearby building or street lights, signage, and reflections of water, coastal glint. An observer, or more pertinently, flying insects, located at a distance, for instance atop a tower overlooking the area, sees the overall illuminated environment from that vantage point. The question arises, how much does the porch's magenta light contribute to the blue light illumination, the kind most attractive to insects, in the observer's view, relative to all the other ambient lights? In this scenario, the porch light is purposefully designed to be blue. Dim magenta lighting implies a bias away from pure blue, and the lamp is physically shielded and directed such that little light escapes horizontally. The lamp sits in a recess, porch ceiling cavity, with a towel shroud blocking direct glare, so most light either goes upward or is diffusely reflected, rather than beaming out. The aperture opening of this cavity through which light can escape is tilted and skewed relative to the world frame, the horizon, and the distant observer's frame of reference. In other words, the opening is not pointing straight out, it might be angled downward or sideways, tilt and yaw angles, and even sheared, stretched in shape, so that from the outside the light's escape cone is very constrained. This geometric configuration means that only a narrow set of directions allow light to escape the porch. Importantly, the wavelength content is also shifted. Magenta light contains some blue, but less than a white or blue lamp would. Together, these choices intend to minimize the porch's output of insect-attractive blue light into the environment. Meanwhile, the environment itself has significant ambient illumination. The transcript refers to 7 wonders with distinct directions, spectra and annular extent superposed on sky glow. In simpler terms, they model the ambient illumination as coming from 7 discrete source regions in the sky or surroundings, each with its own spectrum and brightness. For example, one source might represent the glow of the city in one direction, another could be the moon or a bright star cluster, others could be distant lamps or the reflection of light off the ocean surface, which can polarize and intensify light at certain low angles, a phenomenon referred to as water glint. Collectively, this ambient light, though dimmer than daylight, provides a certain level of blue wavelength background irradiance across the scene, often called sky glow. When referring to the diffuse component, this ambient blue light level is essentially the denominator for the problem. It is the baseline attractiveness of the environment sliding from the insect's perspective. If the porch's own blue output is very low compared to this background, insects would logically pay it little attention, preferring the brighter or bluer sources elsewhere. The measure used to quantify this is the blue-weighted biologically effective irradiance, BDI, effectively the intensity of light in the spectrum that bugs are sensitive to, near UV and blue. We are especially interested in the BDI within the Insects flight corridor near the porch, for example, a certain range of elevation angles and azimuths at. Insects might fly through toward the porch. Analytical framework, geometry and blue heaviness. The research framework outlined in the transcript is highly technical, but its core can be distilled into how geometry, orientation, and filtering affect the fraction of blue light that actually reaches a given observation point or insect flight path from the porch lamp. Key aspects of the model include bullet, coordinate frames and angles. A local porch frame, P, is defined with axes such that V, sub, P slash, sub, is perpendicular out of the aperture cavity opening, X, sub, P slash, sub, along the porch front, and Y, sub, P slash, sub, vertical. The world frame, W, is aligned with the distant observer slash insect's perspective. For example, Z, sub, W slash, sub, vertical, XY horizontal to the horizon, oriented toward the tower, the porch. Aperture's orientation relative to the world is given by yaw, rotation about vertical axis Y, sub, W slash, sub, pitch, rotation about X, sub, W slash, sub, and roll, rotation about Z, sub, W slash, sub. These angles tell us which way the porch opening faces and how it's tilted. For instance, if the porch aperture is tilted upward or sideways, it means fewer rays of light go straight out horizontally. Bullet, tilted and skewed aperture. The aperture might not only tilt, but also be skewed or sheared. In practical terms, shear, parameterized by factors kappa, sub, x slash, sub, kappa, sub, y slash, sub, means the aperture shape is distorted. For example, a rectangular opening stretched in one direction. The effect of shear is to stretch or compress the angular distribution of light escaping. It can be thought of as making the beam slightly astigmatic or broadened in one direction. The analysis treats shear as a linear transform on the aperture before projecting light out. A tilt by angle psi, psi, and theta for yaw and pitch, respectively, will tip the escape cone of light, and shear will widen slash narrow that cone in certain directions. Ultimately, these geometric factors determine the set of directions, call it omega, sub, app slash, sub, from which an insect or observer could actually see the lamp's glow directly. If the porch light is deeply recessed and tilted away, an insect flying outside has to be in a rather specific zone, corridor, to even glimpse the lamp's blue output. Bullet, insect flight corridor, omega, sub, c slash, sub. This is defined as the volume or angular range through which insects approach. For example, the transcript describes a wedge defined by elevation alpha min less or equal to alpha less or equal to alpha max, and azimuth beta, beta 1, beta, relative to W. In plainer terms, you can imagine insects coming at the porch within a certain vertical slice of the sky. Perhaps they tend to fly at certain heights and from certain directions, for example, along the coastline or treetops. This corridor could be hedged, meaning maybe there is vegetation or structures guiding the insect's approach to some extent, hence, hedged corridor. The fraction of the lamp's light that both escapes the aperture and goes into this specific corridor is of great interest, because that's the light that would actually be relevant to attracting insects from that approach. Bullet, blue weighted irradiance, BDI. Insects have a specific sensitivity curve, an action spectrum, peaking in the near UV and blue wavelengths. The lamp's output and ambient light are weighted by this spectrum to compute BDI, effectively a measure of how strongly will this light stimulate the insect's photoreceptors. The lamp's raw power in the blue, P sub, B slash, sub, is considered, along with any filtering. The transcript mentions a tau, sub, blue slash, sub, transmittance of a towel or filter. And aerosol attenuation, air absorbs or scatters some blue light over distance, characterized by an optical depth tau, sub, B slash, sub. So not all the lamp's emitted blue light makes it to the insects. Some is lost in the glass, fabric, and air. Bullet, heaviness ratio, H. This is defined as H equals BDI, sub, local slash, sub, slash BDI, sub, ambient slash, sub. It's essentially a ratio of the porch's contribution to blue illumination at the corridor vs the ambient background's contribution. If H1, it means the porch is blue dim compared to the surroundings. If H were tilde 1 or larger, the porch would be as bright or brighter in blue than everything else, making it a magnet for insects. In our coastal porch scenario, all design choices aim to keep H very low. Ideally on the order of 10, 3, or even less, i.e. tenths of a percent. Using a geometric radiometric model, the research extends standard lighting formulas to account for the tilt, psi, shear, kappa, sub, x slash, sub, kappa, sub, y slash, sub, and the limited acceptance of the insect corridor. For a Lambertian emitter, a light source that emits equally in all directions across a hemisphere, which is a reasonable approximation for a diffusely reflected lamp in a cavity, one can calculate what fraction f of the lamp's blue photons escape into the corridor. In the transcript's equations, f is derived by integrating the lamp's radiance over the portion of directions that align with both the aperture opening and the corridor. In simpler terms, they break f into components. Bullet. F0 equals the baseline escape fraction into the corridor if the aperture was untilted and symmetric, just a reference fraction for a given corridor solid angle. Bullet. M approximately cos theta cos psi equals a tilt modifier that reduces flux when the aperture is angled away. For small tilts, the reduction in projected area roughly follows the cosine of tilt angles. Bullet. Q approximately 1 slash square root 1 plus kappa sub x slash sub 2 1 plus kappa sub y slash sub 2 equals a shear modifier that reduces flux when the aperture footprint is stretched. For small shear, if you stretch the aperture in one direction, its projected solid angle shrinks in another. This is essentially the effect of the aperture's projected area being different due to skewing. Restoring the aperture to a more symmetric shape would increase output. Bullet. U is a corridor coverage factor, 0-1, representing how large the corridor is relative to the lamp's entire hemisphere of emission. A very narrow corridor, small u, means even a perfectly aimed lamp only ascends a small portion of light into where insects might fly. A wide corridor, large u, means insects are coming from many directions, capturing more of the lamp's light. Putting it together, in the transcript they give an approximate formula. F. Corridor. Approximately. F times 0m, tilt angles, times q, kappa, kappa, times x, y, u, alpha, alpha, min max, beta. 1.2. This fraction f, multiplied by the lamp's blue output p, sub b slash, sub, then further multiplied by any transmission losses, like tau, sub, b slash, sub, for the filter, and d, sub, tau, sub, b slash, sub, l slash, sub, for aerosol over path length L, gives the blue radiant power actually reaching the insect corridor. From that, one can derive the mean blue irradiance seen at the range of the observer slash insect, assuming it spreads over a spherical surface area 4 pi r2 at distance r, with some directional factor g, sub, ap slash, sub, if the beam isn't uniform. Finally, converting that to BDI, weighting by the blue action spectrum, and photon energy, yields BDI local. The ambient BDI, sub, m slash, sub, is similarly computed by summing contributions from all 7 ambient sources, each integrated over their patch of the sky and spectrum. The heavy mathematical details aside, the crucial outcome is how small f, and therefore h, can be under realistic conditions. The transcript's example, numeric coastal tower vantage, plugs in some plausible numbers. The aperture is tilted about 20 degrees off axis, yod 10 degrees relative to the corridor, sheared by kappa, sub, x slash, sub greater or equal 0.6, kappa, sub, y slash, sub greater or equal 0.3, a moderate skew, and the corridor is a narrow slot covering about u equals 0.25 of the hemisphere. The lamp's blue transmittance and atmospheric losses are significant, only till 11% of blue light makes it out after passing through filters and a bit of humid coastal air. With a 1W blue radiant output initially, these factors yield f approximately 0.00152% of light escapes into the corridor, and after transmission losses, only till the 0.00017 of that watt reaches the target area. At 5m distance, that results in a very low irradiance on the order of 10.5 Wm2 in the blue. Meanwhile, the ambient BDI equivalent might be on the order of 10.2 Wm2. This example assumed 0.02 Wm2 of blue-weighted irradiance from all ambient sources combined at that wavelength. The resulting heaviness ratio H approximately 5 times 10.5/2 times 10⁻², approximately 2.7 times 10⁵. In plain language, the porch's blue light is roughly 0.27%, several orders of magnitude less, of the ambient blue light level in the insect's viewpoint. This corresponds to the porch being practically invisible in the blue spectrum relative to its surroundings, a blue dim pocket, a midday brighter environment. Thesis statement. This research thesis posits that a strategically designed porch lighting system, employing spectral filtering, magenta/blue reduced output, and geometric confinement of light, tilted, recessed, and sheared aperture, can achieve a local blue light intensity so low that it is outweighed by the ambient environmental lighting by orders of magnitude. In other words, even in a setting with multiple bright sources, anisotropic ambient illumination, the porch remains a minor contributor to the blue spectrum. The central hypothesis is that geometric confinement and short wavelength filtering dominate the reduction of the heaviness ratio, H equals local/ambient blue irradiance, thereby suppressing the porch's attractiveness to light-seeking insects. From a tower or distant vantage, and from the insect's perspective, most insects will ignore the magenta-shrouded porch light in favor of the brighter, bluer ambient sources. The porch thus stays relatively insect-free, a blue-dark refuge, despite being illuminated, validating the concept that local lighting can be engineered to have minimal ecological impact in a bright environment. Supporting predictions and implications. The theoretical framework yields several falsifiable predictions and design guidelines that support this thesis. Bullet. P1. Tilt sensitivity. Increasing the tilt, or yaw, of the light away from an insect corridor markedly reduces the escaped fraction of light into that corridor. The model predicts H will scale approximately with the cosine of tilt angles for moderate tilts. In practice, pointing the aperture more away from where insects are coming, for example facing a wall or upward, will lower the blue flux in their direction, whereas if you rotate the aperture to face them directly, H would increase measurably, making the porch more visible/attractive. This suggests that orienting lights away from known insect flight paths is beneficial. Bullet. P2. Shear/shape sensitivity. Introducing asymmetry in the aperture, the shear factors kappa, sub, x/, sub, kappa, sub, y/, tends to broaden the beam, and thus lowers the density of light in any one direction. Similar to making a flashlight beam wider, it appears dimmer on a given spot. The model encapsulates this by the Q factor approximately 1/√1 plus kappa 2. It predicts that, if you restore a skewed aperture back to a symmetric shape, the light will be more focused, and counts of insects in the corridor will increase, since more light goes their way. Thus, to keep H low, one might deliberately skew the light distribution to avoid hot spots in any one direction. However, too much skew might reduce overall illumination where needed, so it's a balance. Bullet. P3. Ambient source dominance. If one particular ambient source dominates the background, say a bright signage, or a full moon in one direction contributing a lot of blue, then turning that source off would cause a noticeable drop in ambient insect attraction unless the porch becomes comparatively significant. The prediction is that removing a dominant ambient light will reduce overall ambient BDI more than any local changes to the porch would increase it. Conversely, adding a new strong blue light in the environment, for example, a powerful blue beacon elsewhere, would raise the ambient BDI denominator of H, thus further suppressing H, making the porch even more relatively insignificant. In ecological terms, if a new bright light is turned on, insects might flock to that instead, and even fewer would bother with the dim porch light, reinforcing the idea that insects go to the brightest/most blue source available. Bullet. P4. Water glint timing. Environmental factors like water surfaces can amplify ambient light at certain times. For instance, a low moon or sun can cause strong polarized blue reflections off the Ocean. If the moon is below the horizon, even sky glow reflecting on water can create bright patches. The model includes a glint gain factor for sources near the horizon. The prediction is that on nights with significant water glint or any reflective enhancement of ambient light, the ambient BDI rises, thereby decreasing H because the porch's output stays the same but the ambient gets brighter in blue. Field implication. On a night with a bright moon or other sources reflecting on water, insects would even more so ignore the porch. Counts near the porch drop relative to a moonless night. This is consistent with anecdotal observations that on full moon nights, artificial lights often attract fewer insects because the whole sky is relatively brighter. Here the porch is just one more negligible source in a bright scene. Bullet. P5. Corridor size. If the insect flight corridor is narrower, then naturally F and H shrink proportionally, since the lamp's light has to thread an even smaller needle to reach the insects. If the corridor widens, more light can get in. This simply means that, if insects are only coming from a very constrained direction, say a thin gap between hedges, the porch might be effectively safe as long as it's not aligned with that gap. If the gap or approach angle opens up, insects can come from more angles, then the porch's influence on them could increase. So, maintaining or designing physical barriers or preferred flight channels, like hedges, walls, that limit how insects approach can complement the lighting design in keeping H low. These predictions could be tested with deliberate experiments. For instance, one could vary the tilt of the porch light, or alter the aperture covering, and measure changes in insect counts, or light levels in the corridor, P1, P2. Likewise, turning off certain ambient lights, or waiting for different moon phases could test P3 and P4 by seeing how insect behavior, or measured H responds. Methodological notes. To investigate and support the thesis, a mix of measurement techniques can be employed. Bullet. Spectral measurements, M1. Using a simple spectral radiometer or a modified camera, spectral smartphone apps exist, plus known calibration. One can measure the lamp's spectral output and the ambient light spectrum. This allows computing the actual BDI by weighting the spectra with the insect action spectrum near UV/blue. This quantifies how blue-heavy each source is. Biologically, if the porch's BDI is, say, 0.001 of the ambience, that directly validates a low H. Bullet. Photographic analysis, M2 and M3. Long exposure photographs from the tower vantage and from the porch can help assess the geometry. For example, taking a photo from the tower of the porch, while varying tilt could show how bright the porch appears against background. To estimate G sub app slash sub or effective angular output. Another idea is to stand at the porch and photograph the visible sky slot, the patch of sky visible from the lamp's position. This would map out the corridor angles alpha min, alpha max, beta 1, beta by identifying horizon lines or obstructions in the photo. Essentially, it's a way to visually confirm what portion of the sky, and thus what paths to insects, the lamp can actually reach. Anything outside that photographed sky window is blocked by the porch structure. Bullet. Field insect counts, M4. Ultimately, the biological confirmation would be collecting insect attraction data. This could involve sticky cards or light traps placed near the porch versus at a control light. By selectively toggling certain ambient sources, if possible, for example, temporarily turning off a nearby streetlight, one could observe changes in how many insects come to the porch light. If turning off a big ambient light causes a spike in porch insect catch, that supports the idea that previously the ambient was outcompeting the porch. Likewise, if reorienting the porch light causes a change in catches, it supports the geometric factors predicted. These methods bridge the theoretical model with real-world observations, strengthening the thesis that the porch light's design keeps it subdominant in the competition for insect attention. Conclusion. A blue dim refuge in an ambient lit world. The analysis and scenario presented lead to a clear thesis. By combining spectral engineering and Geometric light control. One can create a local light that is spectrally unattractive and geometrically inconspicuous to nocturnal insects, even while illuminating the immediate area for human use. In our coastal porch example, the tilted and skewed magenta light produces a blue-weighted photon budget. The supply of insect-attractive light, that is minuscule compared to the anisotropic ambient field of a typical night environment. As a result, insects at a distance effectively see the broader ambient glow as a bigger draw and largely ignore the porch's faint blue presence. The porch remains a blue dim pocket of light, sufficient for local needs, but unlikely to compete with city glow, moonlight, or other lights in attracting bugs. In summary, geometric confinement, restricting the directions of emitted light, and short wavelength filtering emerge as dominant factors in reducing a light's ecological impact. Even under skewed viewing angles and with multiple ambient sources, the local heaviness ratio H stays very low, orders of magnitude below 1. This means a thoughtfully designed porch light can provide illumination without significantly perturbing insect behavior in a light-polluted environment. The thesis thus provides a framework for developing insect-friendly outdoor lighting. Use fixtures that shield and direct the light where needed, avoiding wide dispersion, and limit the blue/UV content of the spectrum. These measures ensure that our local lights do not outshine the natural or existing artificial background in the eyes of wildlife, thereby mitigating one small part of the broader Allen impact on nocturnal ecosystems. By validating this thesis with further experiments and observations, we can contribute to guidelines for lighting that preserve local insect populations, and by extension, the predators and pollination services they are a part of, while still meeting human lighting needs. 5. Ultimately, creating such blue dim refuges could be an effective strategy to balance human comfort with ecological responsibility in coastal communities and beyond. Let's go mothing. https://marylandgrove.md.edu/2025/07/25/discovering Maryland's moths, the joy of slowing down and looking closer/4 study reveals which outdoor lighting minimizes harm to insects. UCLA. https://newsroom.ucla.edu/releases/outdoor lighting protecting insects. Amazon Basin review current evidence in support of insect-friendly lighting practices. https://www.sciencedirect.com/science/article/bi/S22145745240011884